Since this is the first time I am running a class that is literally just a one-to-one translation of our materials, we'll see how the Python stuff goes. I already know that there's like some quirks with Python, and in some aspects it's going to be a little bit more complicated than the R side, but we can hopefully manage that. Okay, so starting off, because this part sort of takes a while to load up, if you installed Anaconda on Windows and Mac, you should have an application called Anaconda Navigator. And when you open it, it should end up looking like this. And if you want to follow along, I would highly suggest you find Anaconda Navigator right now and then just click it and just let it load in the background. The first time you try to load this up, it will take a long time, and just to save time later, open it now and we'll talk about it later. Just make sure you get this screen. There are a lot of ways that you can open up Python. It's sort of, this is the easiest way in terms of just pointing and clicking, but there are ways to like load it up straight from a command prompt. If we have time later today or tomorrow, I'll show you that, but at least this way everyone can get started in the same process. So just again, if you can, open up Anaconda Navigator. We will be using JupyterLab, so hopefully there's a button that says launch for JupyterLab. If you're coming from Python and from the past and you know how to open up JupyterLab or install JupyterLab, go ahead and install it, and I'll sort of assume that you can get in there. The other thing that is available, if you go to the main setup page, there is a link for a binder link. Where's my chat? So if you don't have everything installed, you can click on this binder instance. And if you need help, like in person, I can point you to it. But you can click on a binder instance. What it will do is it will build essentially the same environment in JupyterLab, and then you can use it in the browser. The main thing to take note is if you lose your session, like if you end up being idle for too long, or you click back on the binder link and not going back to this exact URL, all of the work will be lost. So binder is not, it's like a free service and it's great, but because it's free, like they're not gonna end up hosting your own analytics stuff long term. So those are the two things. If you haven't already, either spin up the binder link now or open up Anaconda Navigator, and then we can sort of talk about the rest as things slowly start to load up, because a lot of that stuff does take a while. All right, so we'll start off as an introduction. So if you just came in, please launch Anaconda Navigator and we'll talk about it. If not, there is a binder link to launch it in the background, and because it takes a while to spin up, you can just leave that be, and then we'll talk about things until we'll talk about things while that works in the background. So hello everyone. This is part of my dissertation research. It's around creating data science materials for people who work in the biomedical sciences. Hopefully you got a set of emails that linked to a set of pre-workshop and post-workshop surveys. So I will be forever grateful if you take the pre-workshop before the end of tomorrow, and then the post-workshop survey sometime after the end of tomorrow. If you took the R workshop, I guess you can also take it, just know that it's exactly the same survey. So you can take it, and then I will figure out how to deal with that part of the data when I get to it. And give me 1 second. This. All right. So Ann Brown is my committee chair advisor, so she's also on the Zoom side of things. So if you need help, you can message her or message me. I also have Zoom open, so I can sort of manage questions on both sides. She works in the biochemistry department and also at the university libraries, and so that's how I met up with her, and we work on part of her work, which is around data science education. For me, one hat that I have is a data science educator. I also have a volunteer position through the Carpentries, which is either teaching workshops for them, teaching instructors on how to teach, and also helping people maintain their lessons at the Carpentries. So if you've never heard about them, they are a nonprofit organization that actually helps put together and train researchers the computational skills that they never learned, essentially. And a lot of the stuff that I am teaching and put together is modeled off of or influenced off of the work that they do. Other things is sort of not applicable for the Python community, but there's stuff in my past around the R community. So that's why the book or the materials that we're working on is essentially a Python and R dual book. For the lesson materials, you can view it at ds4biomed.tech. There is literally going to be a black link to the top that just exists there. For the slides, there is a Google Drive with slides and papers that you can go to and download things if you want. And then for technical terms outside or in this class or outside of this class, there is a glossary also translated in many languages. So if you are just confused or want to know about a definition of some technical term in the world of programming, take a look at the glossary or glossario project. For those of you on Zoom, if you only have a single screen, this is one suggestion on how you can set up your screen. It is tricky because you need to have a copy of the Zoom window open as well as the thing that we're working with. So it says RStudio here, but we'll be using JupyterLab. For those of you in the classroom, your life is much easier because all you need to have is this one giant window here, and then presented on screen is my screen that you can follow along. If you end up going to the website and you end up seeing this page, it's literally because the website is being updated, and the way the website is built is every line of code gets executed and then the output sort of put in, so everything's always working or and stuff like that. So in that process, the website essentially just goes down for some reason. And so my suggestion to you is if you do see this page on the ds4biomed.tech site, wait about 15 minutes, and then hopefully the site is back. Unless I end up sort of doing multiple updates one after the other, but usually I save those updates for sometime in the middle of the night, so hopefully no one's really using it, at least in the United States. The materials that we have put together come from a survey that was sent out before the pre-workshop survey, and the problem that we're trying to address is sort of trying to get you to start with a piece of raw data and using some kind of programming language to work with that data, and then hopefully using that programming language will make your work easier to analyze and easier to reproduce. And from the responses to this set of questions, actually we binned different types of responses, combined it with some demographic information, and we created a set of personas. And so a lot of this book is geared towards one of the 4, even though there's 5 pictured personas. And so You can read about the personas if you would like, but essentially there's 4 groups of people this set of materials is geared towards. Either you're an academic, a clinician, you already program pretty well or in another language or in either R or Python, or you're a student trying to do an analysis of some sort. So there is lots to learn. Replace every single figure that says R and just replace it with Python for this class. All of these drawings are by Allison Hurst, and she is primarily involved in the R community, and she has drawn a lot of figures to help teach R and statistics. And so we're using those figures, but really, they really apply. A lot of these figures will apply to both languages. If you are new to programming, there is a very common set of feelings that you get when your code doesn't work. This happens to everyone, including myself. So don't worry, and then at the end of tomorrow, I will show you a list of resources of where you can go to sort of ask for help or join other communities, and hopefully we can sort of ease the pain of coding that sometimes people go through. Mainly, it's always a question around the computer will do exactly what you told it to do. So if you tell it to do something, it will just be extremely literal, and that's where a lot of frustrations come from. So yeah, so even if you're an R learner or a Python learner, hopefully this sets you up as a small introduction to just getting everything working, and then hopefully you can apply this to your work, and then the more practice you have, and the better or easier this stuff will be. So expectations for today, or really the next 2 days. I don't expect you to write your analysis in R or Python tomorrow. If you end up seeing any one piece that is useful, it is totally fine sort of just using Python for that one little thing, and then continuing your workflow in whatever you're used to. So a lot of where people are coming from is they have a CSV file or an Excel file, and then it goes into either Jump or Tableau, or they do something in Excel, et cetera, et cetera. So there are ways, and I will show you, where you can load an Excel file into Python, do the one thing, and then save it back out as an Excel file. And so you don't have to break or rewrite entire pipelines or analysis workflows. You can very slowly incorporate them as you need. So the syllabus for today, again, I have to remember all of the places where I wrote R and replace them with Python. But we're going to start off with spreadsheets. We're going to sort of introduce you on how to load up Python. If you are using Spider, you can totally use that as a development environment. You don't have to use JupyterLab. But I will be showing you Python with JupyterLab. So if you want to follow along, that's what we'll use. But if you installed Anaconda, there's also a IDE called Spider, which looks a lot like RStudio. And literally just this morning, JupyterLab has a desktop version of it, so you don't have to, you can actually like double click open JupyterLab from your computer instead of going through the process of going through Anaconda Navigator or typing a command to load it. So that literally happened like a couple of hours ago. So I will not show that because I don't even have it installed yet. So that is a few options. And then today we'll show you sort of the mechanics of Python. If you know R, you can ask me questions about how they differ from one another, but I will essentially just go through all of the code from a Python perspective and sort of show you how you can look at the Python documentation. Personally, I find that the Python documentation or Pandas documentation is a little bit easier to find things than in the R world, but then there's like always pluses and minuses between things. And then hopefully by the end of the day, I'll show you how you can run a set of descriptive statistics calculations, mainly like mean, standard deviations, quartile, stuff like that. And then that'll set us up for everything tomorrow on how you can process your data in Python. And then we'll end with fitting a logistic regression model. Like I mentioned in the beginning, I will show it to you using two libraries. I believe we will have time for it. There's a few quirks between stats models and scikit-learn. One of those things right now is stats models will do what you expect as a statistician, and scikit-learn will do what people need to do for just predictive models. And I say that right now because every couple of months there is this huge explosion on Twitter in the Python world when they realize that the results from scikit-learn logistic regression aren't the same as any other stats program. And that is because logistic regression in scikit-learn literally does penalize regression by default. And most people don't know that. And it's literally a parameter that you need to tweak. I need to make sure, I do have to double check that they didn't change that set of defaults, but that is one of those like caveats. And if you compare results, that's like why those two things are different. All right, so we are going to first talk about just managing your data. Like I said, this comes from the set of persona studies that we conducted, and what I found that most people are coming from very little to zero programming experience, and they're coming from a workflow where the first thing that they're given is an Excel sheet. And we will talk about at least getting your data in an Excel spreadsheet, especially if you are curating data from scratch, how you can set it up to be better for yourself in Excel and for any other person you end up working with. So we will take about 30 seconds to do a thought experiment. So let's say you are in charge of collecting data and documenting data for a PK study in a clinical trial. And so what ends up happening is you have patients and they take a drug, and then essentially for the next 24 hours in very frequent time intervals, you take a set of vitals just to make sure that nothing terrible is happening. So here's 3 patients across 40 minutes. These are the vitals that you have taken. And you can either write down on a piece of paper or in your head, how would you input this set of results into a spreadsheet? So assuming that you have a picture of this in your head, I'll go through a couple of examples of what you may or may not have done, and then we'll talk about things that can be done better. All right. So one thing that you could have done is literally each of those values, you turn it into a column, and then whatever the value is, you just dump it into that column. So essentially, it's a one-to-one input of the data that you ended up collecting. So one thing that can be a problem is, although some of these values are self-explanatory of like what they're measuring, not everything is always going to be self-explanatory. So for one example is temperature. Is your data set up in such a way where it's pretty obvious what the temperature unit is? If you're in the United States, sure, we measure everything in Fahrenheit. Temperature is also one of those measurements where it's pretty obvious what unit you're using. Like if we're measuring body temperatures in a human, Anything more than 40 is probably going to be a temperature reading, so you can fix that on the fly if you need to. But it's not really clear, or it's not obvious. If you're working with multiple people, they can end up putting in the wrong thing, or you bump the little toggle button on the thermometer and you're just writing whatever it says. Other things that can be not useful, if you have mixed values or mixed units in the temperature column, you can't off the fly just say, like, give me the temperature column and then calculate an average, right? You can't do that because now there's mixed values and it's going to throw off the actual calculation. Something else that's sort of not as useful, even though you do have blood pressure in there, the systolic and diastolic measurements are both all in the same column. So it's hard to say, if you're just looking for, if the systolic blood pressure is greater than 140, they have high blood pressure. It's hard to do that. You would essentially have to go through every single value in order to do that. So that is little issues that might happen. So I talked about units. So one thing you can do is literally put the unit into the actual measurement yourself. This makes things super explicit. That's good. Certain things, again, like heart rate, like it's probably like beats per minute, and respiratory rate is probably breaths per minute. Blood pressure is probably millimeters of mercury, stuff like that. So certain things, really self-explanatory. Even a pulse ox measurement is, I don't think it's ever anything other than a percentage. But the problem of you putting the actual unit in the column, and you see this problem in Excel as well, is because that column is no longer just a number, you can't calculate an average, right? Excel won't treat that as a number. So even though it's nice that you put that unit information into your measurement, one, it might be tedious. You might forget it anyway, but more importantly, you won't be able to just say, calculate the average. Another thing that's sort of what you will probably end up doing is separating first name and last name, depending on the ethnicity, ethnic background of the name. Sometimes this is harder to do, but usually people end up looking for or sorting people by first name and last name. So that is another thing that you want to think about. And the splitting thing is also the same thing that happens with blood pressure. You want to be able to split things if you can, and not combine things into a single column. This is something that ends up taking more time, or something you have to keep in mind as you are inputting data manually, but it's one of those things that could save you time later on. And then in tomorrow's class, if you do end up putting some kind of marker or breadcrumb for yourself, like blood pressure, like I can easily fix the blood pressure problem because there's a slash between the two numbers, and I'll show you how you can deal with that. A little bit harder for like something like first name, last name, because you can't just use the heuristic of like, the first name is gonna be one word, and if I see a space, everything else is the last name, right? So that's much, much harder to do. Even if you do last name, comma, first name, or like punctuations and stuff, like don't always rely on like, yeah, I'll just use the comma as the separator. Like names kind of get weird. Periods are another thing that get weird in names because you have things like junior and senior, and then names get weird. So if you can just input things correctly the first time, especially if you know that's going to be a column that you're going to be working with. So I talked about units. One thing you can do to sort of make a good data set that is self-explanatory is, instead of just putting the unit in the actual data itself, just make the unit part of the column name. That way it's really explicit. You only have to type it once. I would go, if you know this is going into like a programming language later on, I would also say like make everything lowercase, don't have spaces, use underscores instead of spaces, and then your life will be much easier later on, because this is supposed to be raw data and not like a visual representation to make things look pretty. If you are working with units and you end up knowing that it's going to differ depending on some kind of measurement, I don't know of a great example off the top of my head, but you might end up in a situation where, like, if the number gets too big, the machine automatically changes the underlying like order of magnitude for you. So in that case, if that is the case, sometimes it is appropriate to put the column or that particular variable's metadata information in a totally separate column. So then you can look through or find things or search for it completely separate from the actual data that you want to work with. Right. And so the main takeaway is really, if I were to look or open up an Excel spreadsheet and I click on any single value, there really should just be one thing in that cell. And so that means that for a particular column, everything in that column should only represent one unit of information, and I shouldn't be able to say like, oh, that thing is actually a measurement of like 2 other variables put together. Right? And we'll see this point come out essentially throughout the next 2 days. All right, so let's say you have that data set that you put together in your head, and you are maybe you've made some changes from what I said, and this is a PK study. So let's say, 12 hours down the line, and then 24 hours down the line, here are 2 other readings. Yes, there's usually like a reading like every 5 minutes or 10 minutes, depending on what time you took the drug. But let's say we're just trying to add 2 more units of information. How would you incorporate more bits of information with the foresight that it's not just going to be these 2, you're going to have like tens or hundreds of other readings down the line? All right, so one thing you could have done, and there's really nothing that I am going to say is like something that can't be fixed. So one thing you could have done is for each one of your patients, you created a separate Excel sheet or a tab in an Excel sheet. And that's totally fine. And then insert like everything I said about column names and units and all of that, assuming that's all in a format that you're happy with. There's nothing wrong with that, and if it makes and I would also say that if it makes your data entry easier, I would always go for that, because as you're inputting data, you're probably inputting it in a way that's easy for you, and easy for you also means that it's easy for you to spot check what's going on. The main thing here is if each of your patients are in separate data sets, you don't have an immediate way of saying, I want the average systolic heart rate across all of my patients on like time 0, right? And I need to flip the labels for between systolic and diastolic. That is something I keep saying that I keep forgetting to do. But that is one thing that can get annoying when you start splitting things up. If you end up with putting everyone into one single Excel data set and as in separate sheets, this might work because there's only 3 patients, but it can get overwhelming if you have tens of people. You will have tens of sheets, and that can get annoying to work with, just because the single file just ends up getting bigger and bigger, and you have to scroll through and open up separate tabs. So instead of having everyone into separate tabs, one very common thing is you put everyone in the same Excel sheet, but then you use new lines or empty lines as a visual marker to like separate your patients. And this does fix the problem of I can totally select a single column and calculate averages, or I can select a column And I think in Excel, like by default, it'll give you the a count of the number of non-missing values. So like you can visually spot check a lot of those things. But if you load this into a programming language, all of those new lines come up as like brand new observations, as missing values. And one thing that you have to remember, if you do things this way, is probably the first step is to like delete all of the missing values. Depending on the function that you use to calculate mean, or if you end up writing your own function, you have to be very careful about how it handles missing values, because now if I say, give me the average heart rate across all of my patients across this entire data set, if you write your own stuff, is missing values automatically getting converted to a 0, and then now your averages are totally like you're adding zeros and incorporating them into the denominator? That is something that you have to be very mindful of. So using these visual markers, again, it's something that you will end up doing because it is a data set that you're putting together, and it makes separating people easier. I would almost suggest like don't do this if you're doing it in Excel, because Excel does have a data sorting feature. So you can, if you really want to group people by first name or last name, just so you make sure you have everyone, you totally should just use the Excel sorting feature then, instead of relying on visual breaks. And this also counts for making one-off calculations in Excel, which is something that's really easy to do. But if you do end up saying like, oh, this little cell off in like G15 is the average of this, when you load that into a programming language, that's going to count as part of your data set. And so you're going to end up with a whole bunch of missing stuff, missing values, and then this random number somewhere. And then that's also things that you have to think about. So if you have a rectangular data set, leave it as a rectangle and don't make it like some other weird polygon of data. One thing you do want to be, and this is actually something that like I would say like much harder of a problem to fix, but all of the examples I showed you were putting your data like one set of data below another set of data. What you really want to avoid is putting one set of data next to, like as a separate column, to another set of data. In this case, it's really obvious why you shouldn't do that, because you're going to end up with like repeated column names, and that just ends up being a headache in general. But if you ever end up in a situation where in order to add new data, you're creating a brand new column to add that bit of data, think very long and hard about how many times you're going to end up doing that. If it's like, oh, I have a new actual variable that I'm going to calculate, that's fine. If it's time series data and you're adding like another day of values, think about how many times you're going to end up doing that. And I say that because very recently, like within the past year, if you didn't know, the UK COVID tracking system it pretty much broke one day because Excel ran out of columns, and they were using each day as a new, each column as a new day of the pandemic. And so Excel ran out of columns. All of your data products were built on this one Excel spreadsheet, and it stopped updating. Or the last column ended up either not adding new values or replacing existing values, and then models all broke because there increasingly became bigger and bigger gaps. And so if you didn't know, yes, Excel actually has column limits. It also has row limits. And so you want to be very careful if you start tacking on information column-wise. Even if you end up working with databases, individual tables in databases also will have column limits, and that's another thing to tell you, like you should probably not store your data column-wise if you know it's going to be something that ends up growing. So it's okay if it's just, this is the data set. It has like 100 and whatnot columns. Like if you have genomic data and each column is a SNP, like that's fine. That you're not adding more SNPs to this data set. And so that's something that you really do want to be mindful of. So one solution is, if I'm just being sort of thorough, is make sure your data set is really just all in one rectangular data set. Put it in chronological order is probably the order that you're going to be capturing results in. And if you are in Excel, utilize the sorting features to like double check your work if you need to. But this way, it's in a format that like you can just give it to someone else and then, or yourself, and you can continue on with the analytics steps without having to worry about like combining data sets if they're like in separate files. It's just all there. And then if you really need to look at subsets, either use the filtering feature in Excel, or I'll show you how you can use the filtering feature within Python. So as long as you plan for things like leaving slashes between systolic and diastolic, or like underscores between first name and last name, as long as you have some heuristic of like, I know how to deal with this, and this is how I will deal with it, it'll make it feel less of a problem, and you won't have that feeling of like, this data is all messed up and I don't know how to deal with it. All right. So hopefully, before I go on, hopefully by now, this has loaded up in your background. If not, like, just let me know. And hopefully it's been long enough that I'm pretty sure it loaded up by now. So hopefully Anaconda Navigator is working. Another part of this exercise or thought experiment is a lot of clinical trials will present adverse event criteria. And so let's say you have this set of criteria that needs to be reported because something happened, and this is probably not a good thing. How would you take this bit of information and add to your data set on whether or not an observation needs to be reported, or something happened and you need to flag it for yourself or in the data set? So one thing that you probably thought of doing, and I usually end up doing this too if I end up staring at the raw data set, is as you're going through and if you have the adverse event criteria memorized, you just end up literally like bolding or color coding the value straight into your data set. And this is useful in the sense that it will stand out. So if you end up using green or red background colors or something, it's a pretty quick way just to figure out like what exactly is going on. The only problem is if I were to load this into any other piece of statistical software, that color information probably won't carry on with the value that's stored in there. So that 142 or that 101 heart rate reading, when I load it in, will just stay as 101, and the fact that it has been flagged as red probably won't show up. And if I also look at the 101 in this particular data set, if I look at that specific value, there are two things that are encoded in that cell. One is the actual heart rate value, and then the other, because of its color, it's telling me whether or not that's a quote-unquote bad value or something that needs to get looked at, right? And so that first thing about each cell should only contain one bit of information, you sort of broke that rule by putting color into it. And so one thing you can do is you can still have color and mark that value with red if you want, but if you do know that you're going to load this into a data set, really just make one thing that you can do is make another column that is metadata for that, either that observation, that entire row, or that specific value. So this might explode your data set in the sense that you might have heart rate and heart rate like AE. And then you might have different values with an AE like underscore AE for all of them. Maybe that's annoying. That's something you can do, or you can sort of leave a marker for yourself just so life is a little bit easier down the line. Just say like, this is some row that needs to get looked at. Chances are, if you filter on the rows, you probably can read across and figure out like what's the actual problem. For most clinical trials, adverse event reporting, it doesn't matter what, like this is just the event, and then you have to do this whole thing about what happened anyway. So this is one way where you can sort of utilize using columns as metadata and just put everything into the same data set and not just using colors or something else to capture that information. And so that really goes on to one of the last points, which is we talked about your raw data, and everyone always talks about like, yes, my study would be so much better if I had access to the raw data, but then they treat that raw data set as like a visualization, and then they sort of like have this Excel sheet that is many colors, that if you give it to someone else, like all of that color coding information doesn't get loaded up, and so you have to end up undoing all of the work that you did, like making colors and stuff. And then the last exercise is really sort of just what happens if you want to end up taking notes about a specific column. And the main takeaway there is like, yeah, if you are curating results for yourself, it is probably a good idea to leave yourself like a notes column just so you can take notes about what's going on. And then that's another way where you can have your metadata travel with your data set. One of the things that's really nice about R and Python is you don't always have to have a code book traveling with your data. So like if you have a column that's like smoking status, a lot of times if you end up downloading data, the column values are going to be like 0 for no and 1 for yes. And for stuff like that, if it's like a yes/no question, hopefully they coded it as 0 for no and 1 for yes. But with a lot of these programming languages, you can literally just have smoker or non-smoker, and then your data set itself is self-documenting. And if you end up curating your data set, just make it self-documenting so you don't have to carry a code book with it, because sometimes you might forget, and then as emails get passed around, people end up not knowing what's being stored in your data set. Right. So as a summary, spreadsheet programs are totally fine. If you ever hear someone like say Excel is bad, you should never use it, that's not necessarily true. Inputting data is probably one really good use case for using graphical user interfaces like spreadsheet programs in part of the data analysis process, because that's how you input data. If you've ever had to input data strictly through a programming language, probably not fun. And it's really hard to check your work, especially if you're live encoding data on the fly, if you're doing that input in a programming language. But just as long as you identify like certain things shouldn't be done in a spreadsheet program, like turning your raw data set into a visualization, probably not a good idea. Like make your visualizations like not part of the rectangular data set is probably like the thing that you should do. Even in Excel, I would also say like, yes, it's really common that you make those one-off calculations. Like there's ways to make it so those calculations are on a separate sheet, so you don't mess with the actual rectangular raw data set portion of it. All right, did you have a? Oh. All right. Okay, so we are going to launch JupyterLab. Before we do so, hopefully, hold on, let me just open up the actual page. So part of the setup email, or part of the emails that you've gotten, there was this section on data sets. And if you go to this link on that part of the page, and I will copy it there, this is the repository that has the data that we'll be working with today. The way you can download this, if you haven't already, is you click on the little code button, you download the zip file. For me, I'm going to do this on the desktop. The more important thing is when you download the zip file, please unzip the file. Just because it opens when you double click it doesn't mean it's a functional folder that you can use. So if you end up with like a weird error, that is definitely the first thing that you want to end up checking, and definitely make sure that you've unzipped the file. Once we're there, hopefully Anaconda Navigator is open and running for you. And what we can do is click on launch, and it will launch JupyterLab in whatever your default browser is. All right, cool. Okay. So once that is open, you should end up with a page that looks like this. And I believe you should only have one option, which is Python 3 under the notebook section. So what you can do is click on the Python 3 button under the notebook section, and you should end up with a page that looks like this. On the left-hand panel of the folder, so I literally ran this version of the class the last 2 days, so I have all my R files. But on the left-hand side, you will have access to all of the folders and files in that zip file that you unzipped. The most important one being that there is a folder called data. And one of the things about, it's sort of nicer in the JupyterLab world, is a lot of times when you end up working with other people and you have a folder for like this entire project, you need a way or a consistent way where you can point to the data in that particular folder. So we need to go through a small aside about how to find files on your computer. So regardless of if you're on a Windows computer or on a Mac or on a Linux computer, every single file and folder on your computer has a location. That location is called a path. And so right now, my ds4biomed folder is on my desktop. And so if I were to create a brand new file in this folder, so let's say it's like the load data file, how do I point to the data, the medical data tumor growth file in the data folder? So there's two ways you can point to that. One is known as a relative path, and then one is known as an absolute path. A lot of times, and I saw this a lot when I was working with people who worked with SAS, where you have like a libname call in the very beginning, and everyone puts in like, here's the folder, that's my working directory, and chances are if you share that script with someone, like you have to modify the first couple lines to make it work for your own computer. That is because they are using what's known as an absolute path, and that is the like complete address to the file on that machine. So that means if I were to give you this folder and your name isn't Daniel, you probably don't have a username folder called Daniel, and that's why computers can't find things when you start using absolute path notation. And it's most likely because you put the folder in a different, it has a different address. Either your name isn't the same as the person, or like I put it on the desktop and you decided to put it under a folder called projects, right? So that will change the absolute path. The relative path is relative to some starting location. That starting location is known as the working directory. And so one of the most important things, if you can find the file on your computer and some reason the computer in the programming language says file or folder not found, this is the thing you want to check, is what is that program's working directory? Because relative paths are always from here, where do I go from here? So it's all relative. And so let's say, for example, I move my file into a folder called analysis, and now my working directory is the analysis. How do I refer to the data folder, which essentially I have to go one folder up, and then to the data folder, and then to my actual data set. So for computers, the way we say one folder up is using two dots. So dot dot slash, if you ever see that, means from some starting directory, go up a folder, and then you can specify the path going down. In this particular example, because the working directory changed, the relative path needed the dot dot slash in front, but the absolute path, because I didn't change where the medical data tumor growth folder is, the absolute path hasn't changed, right? So there are reasons why some people use absolute paths, because you can move your analysis file around and the absolute path won't change. But the relative path is more useful if you're collaborating with other people, because then the entire folder project can move around, and then people don't have to change bits of their code. So how do we actually start? You can write it on a piece of paper or in your head. Let's say you are in the, you have a folder called projects. There are two projects in this that you're working on. One is a chart review project, and the other is some randomized controlled trial. They both have data folders with a patients.csv file, and you are working on the chart review, which is some demographics file that you're working on, but you end up needing both of these patient CSV files. Maybe you're just saying like, hey, like this is, the RCT folks are also part of the chart review because it's all part of the same clinic or whatever. How would you refer to both of those CSV files? So for the RCT folder, how would you refer to that one as a relative path? And then how would you write the absolute path to the data folder in the chart review? And I'll sort of give you about a couple of seconds to write it down or think about, and then hopefully your solution's correct. So the first part of the question is, what is the relative path to the patient CSV file in the RCT folder? And so if we're starting from the analysis folder in chart review, we have to go one folder up, so it's dot dot, to the chart review folder. And then from the chart review folder, we have to go one more folder up, so it's another dot dot to the projects folder, and then we can go down to the RCT folder, then data, then patients. For the absolute path, you start with whatever your computer's starting point is. So on a Mac and on a Linux machine, it's always going to be this /. On a Windows machine, it's probably C:/ or whatever letter that you're working with, / to specify the absolute path. One thing to note about Windows is you can always find the path to a file. So if you have Windows open and I am in this ds4biomed folder, if you look at your Explorer, you can click on this and it will give you the actual path that you can copy, which is really useful if you just need something to quickly copy and paste. The only problem is if you use this part of your code, every other programming language and system sees this backslash as something entirely different. So if you copy and paste that slash into programming languages, you typically have to put 2 of them in there, or you find and replace and turn the backslash into a forward slash. So that is typically a Windows-specific thing that you have to do. Okay, so let's load up our first thing before we go on like a quick break, and then if things aren't working, we can deal with it during our break. When we opened up Jupyter Notebook, it will by default have a name called untitled.ipynb. If we right-click this, we can rename the notebook. And another thing that's really useful is I highly suggest that when you are working on analysis projects, if there's a specific order you expect these people or yourself to either go through your analysis in, like pre-pend your file names with a number. So this way, if I, for example, have an analysis script and a cleaning script, if I sort them alphabetically, it's going to look like you do the analysis first and then you clean your data, versus if I say 0, 1 clean and 0, 2 analysis, it'll sort properly and it'll make your life easier trying to figure out, oh, I haven't seen this project in a while. There's 10 files in here. Which one do I do first? You don't have to guess about what that process is. Another thing I also suggest is you either use 2 digits or 3 digits in your naming process. If you use 2 digits, that's fine. If you use 3 digits, count by 10s instead of count by 1s. And that's mainly so if you've occasionally realized that computers will go from like 1 to 1, and then the next number is going to be 10, 11, 12, and then it's going to hit 2, and then 20, 21, 22, 23. And it's because it's sorting by the actual like dictionary order, not numerical order. So if you keep things as double digits, it'll fix that problem. I personally do things in 3 digits and count by 10s, and that's because I go from 10 to 20 and 30, and if I forget something, I can make a 15 without having to rename everything. So that's something that I do, and it really just makes just setting up your projects like way easier for yourself and other people. Okay, so we're finally ready to do the analysis part and loading up our first data set. In Python, we are working with a library called Pandas. Pandas is an acronym, if you didn't know, that stands for panel data, which is from the economics world and Stata world is really time series data. So Pandas really was originally made to work with time series stock data. It was created at a hedge fund, so that's sort of the reason why it's really good at doing time series related operations. So Pandas is a Python library, but it doesn't just open when we launch Python. So we have to load up the library. The way we load up things in Python is we write the import command. So we can say import pandas. And in the Jupyter Notebook, you can either click the little play button and you'll see the little star calculate. And once it turns into a number, then it's been executed. What you'll see me do a bunch is using Shift Enter, and it will execute that line and then open up another line underneath. If you're sort of testing something over and over again, instead of Shift Enter, you can hit Control Enter, and it will just give you the prompt back again, so you're not going to the next line. One of the things you have to be very careful of when you're using the Jupyter Notebook is you can execute code out of order. It's not always apparent. So like if you want to do something twice, you can run the same block twice, but that's not the same thing as your code running that code twice from top to bottom. So that's something you have to be very careful of when you're using the Jupyter Notebook. And That's probably a reason, if you've ever taken another Python course before, why some people don't use it, and it's because of that execution order. So one thing you want to do regularly is under the kernels tab, you want to occasionally, when you're done doing something, either click restart kernel or restart kernel and run all cells. And what that will do is, this is the equivalent of turning it off and turning it back on again. So it'll turn off Python, turn it back on again, and then from the top execute everything in the order that you wrote it in. So this is something that you definitely want to do occasionally, just to make sure that your code is actually executable to someone else and not just you jumping around and trying things out. All right, so we're going to load up our first data set. Give me 1 second. So pandas is a library. Think of it as just like a big book of functions that you can use. One of those functions in pandas is a function called read_CSV. And so how do we tell pandas to use that function? We say pandas because we're using that pandas library. We use the period. So in Python, the period essentially means like open up that thing. So using pandas, we're going to open up the read_CSV function. It is a function, meaning it's essentially a command. Commands have a pair of round brackets in them. And the way read_CSV works is in either single quotes or double quotes. For this part, it doesn't matter. You put in the path to the file that you want to load. So all of that talk that I talked about paths, this is where it comes into play. My current working directory is where this file exists. So it's this ds4biomed-learner, that is where this notebook file exists. That is my current working directory. So for me to go into the data folder, all I need to say is start from there, go to data. Python and Jupyter notebooks, and depending on your IDE, is useful that if you start typing in like the path of a file and you hit the tab key, it will essentially try to open up the folder for you so you can view it. One of those things, so the data set that we're looking for is medical data_tumor growth.csv. So if you end up in a situation where like this is where my file is, and if you hit tab and it doesn't pop up, it's probably because your working directory is not what you think, or you type something wrong beforehand. And so this tab completion is really useful because it will prevent typos from happening. So once we have that, all we need to do is run that cell again by either hitting Shift-Enter or Control-Enter, and we'll load up that data set. And you'll see the first 5 lines and last 5 lines in that data set in Python. So hopefully that worked for everyone. The next thing, at the top, I wrote import pandas. But you'll see on the internet, the other way of loading up the library, or this particular library, is import pandas as PD. And what this means is instead of writing pandas every single time I want to call a function out of pandas, I can replace that word pandas with the alias PD. And so now pd.readcsv instead of pandas.readcsv is the reason why you'll see this notation a lot more on the internet. Okay, so we have that. Let's take a 5-minute break for water, whatever you need. So for me, it's going to be 13 past the hour. And then if you have an installation issue, like now is the time to let me know and we can try to figure it out. But take 5 minutes, come back at 13 past the hour. there anything specific that like you need, like Python-wise? I can like try to shim it in like between today and tomorrow.
I don't know. Like, I've never used Python and don't know anything about it, other than like it's how our lab is going to end up doing some programming for the tasks that we're running during an fMRI scan. Yeah, that is all I know about it.
Okay.
So yeah, so I don't. It's hard for me to identify like what I actually need, because I think that we weren't really going to be using it much for the like statistical analysis side of things. Yeah, more
Um,
for
okay. I guess because, is it for that study that's like posted down there for the, I don't know, there's like a little flyer for an fMRI study.
There's a bunch of those going on, and I think other labs probably use Python already to do it. But yeah, we use it. We're going to be using it to, like, we give people little sips of drink while they're in the
Oh, okay.
fMRI scanner. So we're going to use it to program the timing of the pumps
Oh,
that
so, okay, so you're
sensors
using it
and
for
yeah,
like hardware
yep,
things. Okay.
yep,
Yeah,
exactly.
that's one of the things that Python can do that R
Yep.
cannot do at all.
Right, yeah. So that's like that is our overall, like that's the reason that we're using Python and what we're trying to do with it. So yeah.
So are you planning to use it for data collection at all, or is it literally just microcontroller programming?
Right now, as far as I'm aware, it is it's just
The
the
controlling the
controlling
pulse?
of
Okay.
the yeah, of
A
the
lot of this might not apply.
yeah, yeah, that's what I'm thinking. Yeah, so I'm
um,
wondering because like yeah, so our other data collection comes from I mean, I guess eventually maybe we're going to be using it for like fMRI analysis.
mhm.
Right now we do that in MATLAB.
Yes.
So
That
maybe we will be doing that with Python later. Maybe, because I think MATLAB is, I'm not very good at it. I don't know very much about it, but I think
it's
it's got
it's
some
very so once you get to the point in
features.
MATLAB, this will apply.
Do
Um,
what?
this stuff will apply when you get to the MATLAB portion of it.
Yeah, yeah.
Um, maybe I mean I'm also guessing Python's like a very it's hard to teach. I find that it's hard to teach Python because some people use Python for like non-data related work.
Yeah,
Like
yeah.
people use R for pretty much just data related work.
Yeah.
Um, but when you end up with sensor data, you
Mhm.
probably are your data probably is nothing but numbers,
Yeah.
and it's probably all like you're probably MATLAB. You're probably just doing random transforms of whatever to do the analysis. Um, Pandas is made for things that come out of spreadsheet data, or
Mhm.
another way of phrasing it is it's for heterogeneous data where each column is like it doesn't always have to be a number.
Yeah.
A lot of sensor data is like here's literally a matrix of numbers, and
Yeah.
then you treat everything as a matrix operation. Um, so Python pandas itself lives on top of a library called NumPy, and that is the matrix library that Python works in. And then pandas sort of is like, okay, sometimes not everything's a number, so we'll make a whole system
Yeah.
to deal with not number things.
Numbers. Yeah.
Um, so that's sort of where it applies, because eventually I'm assuming once you get to sensor data, you want metadata attached to it. Um,
Yep.
and that's when pandas comes
Yeah.
into play.
That makes sense.
Okay, so I didn't see or hear anyone having an issue, so hopefully no one has an issue, and if you want to follow along, you're following along. All right, so what we ended up with last was we loaded up a CSV file, and it dumped the contents of that file to the screen. By default, if you're in the notebook system, if it realizes that this was a data set that you loaded, it will show you the first 5 rows and the last 5 rows and some subset of the column. So it's if you have 1,000 columns, it's not going to show it all. And the reason for this is a good way to make sure that your data got loaded up properly, especially the first couple of rows, or really the first row, to make sure that your column names got loaded up correctly. So if you loaded things up from Excel, maybe the first row in the Excel file is like notes. So there are ways to say like skip the first 5 lines in this file and read the rest, or like this data set doesn't have column names. Don't treat like the first row as columns, as a column name and stuff like that. And so if you're working with sensor data, like you probably don't have column names. And it's literally like this is the 256 by 256 picture reading. So you want to be careful on how you load in that data, and looking at this very quick view is a good way to just make sure your data got loaded correctly. The next thing is it's not really useful to have this data set loaded or to reload the data set every time you want to do something with it. So in Python, we can create objects or save that data set into a variable. So we can save this into a variable called tumor, use the equal sign to assign it. So tumor equals the contents of that CSV file that we loaded in. And then we can, if we just run the command tumor, like that variable, it will now present itself, present the contents there. If you have Excel files, so let's say I want to load in a data set for tumor. I'll call this _Excel. And again, computers really don't like spaces, so you will get into a very big habit of using underscores in lieu of spaces. And I realized I forgot to plug in my laptop. That can also explain why it's running slow. Okay, so if we look at PD, so this is pandas, instead of read underscore CSV, if we look at read underscore and then hit tab, so remember tab is the computer's way of trying to be useful so you don't have errors. One thing you'll notice, there is something called read clipboard. So if you have an Excel file or something and you copy like a small rectangular part of the data set, you can actually read straight from your clipboard into a data set into Python, which is really cool. One thing, I showed you read CSV, but another thing that's built into Python is the function called read underscore Excel. And this looks exactly the same as the read underscore CSV function, except now we need to put in the proper file extension for Excel files. By default, it will load up the first sheet in the Excel file, but if we hit comma and then hit the tab key, sorry, if we hit comma and then the shift tab key, we get the little help documentation for this particular function. And so reading things into programming languages there are a lot of like exceptions. So you'll see that like the next thing people usually try to read is like the sheet name. So by default, it's reading the first thing. In Python, everything starts counting from 0. That's not always the case in every programming language. I think MATLAB counts from 1. So translating code is like a thing that you have to be very careful of when you're trying to like pull things out. But the first thing you can specify is a sheet name. So I believe you can give this like the name of the sheet or the actual position of the sheet, and it can load things up. There's other things like skip rows, like how many rows you want to skip. There's other things like in a lot of health data sets, 88s or 99s stand for like missing value, or person did not apply, or person didn't want to respond. There are different, you can load in data sets and just treat all 88s and 99s as like missing values coming in. That's something you can do. One thing that's happened to me in the past was I read all 99s as like a missing value, and then I also didn't realize at the time that there was an ID column that went from 1 to like 300, and 99 was a number that got read in as missing. So that's something I eventually caught because programming allowed me to see that trail. But if I ended up doing that in Excel and did a find and replace of 99s and replaced it with an empty or a 0, probably much harder to figure out like what went wrong. So that's something where you can, if you are cleaning data, it's best to try to figure out how to do it in some reproducible way versus like doing it and modifying the raw data set. So if I run this command, you might get an error depending on how you have Python installed. Read Excel requires like another dependency, but I believe Anaconda does ship with it. But if you run read Excel, you should end up with the same data set from when we loaded up the CSV file. All right. One thing when you are working with objects in Python or in whatever language, one really useful function that's not pandas specific, but this is Python specific or Python related, is there's this built-in function called type. And if you ever have a variable or something and you don't know what's going on, running the type of something will tell you what this object is. So you see here at the end, this is a pandas core frame data frame object. Essentially, this is telling you that this is a data frame object. And once you're given a data frame object, you know you have this rectangular data set as if you are looking at it from a spreadsheet. If it says something else, that is something that you might want to check if like this code isn't working. Probably if you expected it to be a rectangular data frame object and it's not a rectangular data frame object, that's probably a reason why your code isn't working. And so this is a really good way to like slowly start to debug or figure out or ask for help when you're working with this stuff. All right. One thing that you can do in Python is given a particular data set, so tumor, you can run a function called info with round brackets. So what is going on in this notation? This is saying, look in my tumor data frame object. So this is the data set I looked at. This is a data frame object. This data frame object can do, it knows information about itself and it knows how to do things on itself. One of those things it knows how to do on itself is to calculate some basic information about itself. So in order to tell it like, hey, I know you can do a bunch of things. One of those things you can do is info. So I open up that feature by using the dot notation. So it's very similar to saying pandas.read CSV. We're now saying like, hey, you tumor data set, calculate your info. And this is another way that you can quickly spot check what's going on with your data set. You'll see that this is a data frame object. It's got 574 entries. These are your column names. These are your column types. And this is telling you how many non-missing values there are in that data set. And then if you really want, this is an estimate of how much space is taking up on your computer, in the RAM that it loaded up. So now that we know that like, okay, this data frame object knows information about itself, there is this difference, there's a small difference between things it knows how to calculate about itself and then just things it knows about itself as an attribute. So another analogy is like, I am a person, so that is like a thing. I know something about myself, like my name, so my name is Daniel, but I can walk, right? So there's a difference between like me knowing my name and me doing the operation of walking. So calculating something like info is like me doing the operation of walking, and calculating something like, or telling you something about myself, like my name, is known as an attribute. And I mention that because tumor, or all data frame objects, have an attribute that it knows about itself, about how many rows and columns it has. And one of the things in Python world is there is a difference between an attribute, like shape, and then like methods, like info. And I'll show you the documentation on where you can find those two pieces, but that is sometimes why if you end up forgetting you get an error message. And it's because you told it to calculate this as a function, and that doesn't exist. So that's another thing you have to be mindful of as you're like literally typing your code. And you can tell yourself mnemonics, but this is going to be a common thing where like you forget, like, is this an attribute or a method that it knows how to do? All right, so we have this data set that's loaded. One very common operation is I have this data set and I don't exactly need all of these columns. Or I want to pull out a single column because I need it for like a particular calculation. So if we look at the tumor data set, one of these columns is called size, right? And so let's say, for example, I only need the size column in my data set for like later on. The way you pull something out in Python, the syntax is using square brackets. And so if I want to pull out the size column, I use square brackets because that's the notation for subsetting or pulling something out. And then in single or double quotes, we put in the name of the column. And so that's how we can pull out just that sequence of values. If we want to pull out multiple values, this is where the notation sort of gets a little bit weird. In Python, if we want to specify like a list of something, like multiple objects, like all in one container, we also use square brackets. So if I want to pull out size, if I want to pull out the columns group with a capital G, day with a capital D, and size with a capital S, I need square brackets to say, hey, this is a list of values. And then I pass that list of values to the outside square bracket, which means this is what I want you to use to subset. So if you've ever been confused why, like in pandas or in this notation, there's always two square brackets going on, that's why. And this is how you can subset based off of the columns that you want. So if you are working with like genomic data and you only care about like a few of the columns and not the entire genome, you can use this method to sort of help you select just the data sets that you need, so you're not loading up everything all in one go. One really subtle detail that exists between this line of code and this line of code, if you look at the output between these two bits of code, you'll notice that the one on the bottom looks a little prettier than the one on the top. Like the one on the bottom looks like a nicely web formatted table. And then one on the top looks like if you've just programmed before and it's just like, here's dumping you a bunch of values. So if you are working in the Jupyter IPython ecosystem, you can use these visual outputs as cues for what object that you have. Because if I remember the type function that I just gave you, if I run type around that first function, it is no longer a data frame object. It's known as a series. So you can think of a data frame object as a spreadsheet Excel file. That whole thing, that whole data set is a data frame object. Each individual column has to store the same type of information. So it's either all characters, or all strings, so a mix of characters and numbers, or just characters, or it's just numbers. So like integers or floating point numbers that have decimals, et cetera, et cetera. So each column needs to store the same type of information, and each column is called a series object. So like a data frame is composed of multiple series, and that's sort of how these parts relate to one another. So the visual cue you get for like, how do you know you have something called a series? Well, if you look at the output and it looks pretty and it says like rows and columns, that's probably a data frame object. And if it says like length of this and it gives you the actual type and it prints out in this less prettier format, it's probably a series object. And I mention that because if you are building like tools, or you need something that's like always giving you a data frame object, If you pass in a list of one item into the way it subsets, it will always give you a data set instead of just a sequence of numbers. So another way you can think about it is a series is a vector or a sequence of numbers, but a data frame is like a column. Okay. So that's how we can subset columns. The next important thing is how do we filter on rows. All right, so we have our data set, tumor. The way we can filter our data set row-wise is we use the period. So instead of using square brackets, because that notation is by default selecting on columns, we use this notation called LOC for location or locate. And this says, hey, tumor, go look up something about yourself. One of the things you know about yourself are locations about things. Now that we're telling you to work on how you locate things, now I want to do a subset on that, what you know about that. So that is this is the syntax for tumor or for filtering rows, is using this .loc and then square brackets. More technically, this is also known as an accessor, like you access this data frame object in by its location. So this is also known as an accessor. So let's say, for example, I want to filter my data set such that the values for a group is equal to 1. So the tumor growth data set is a mock, or it's not a mock, it's an actual data set of, for different treatment groups, for different treatment groups and days into the treatment for a particular person by ID, what is the size of the tumor? And so and we know that group 1 is the actual control group for this study. So let's say I want to just look at the control group for my study. So maybe you're given a big data set and like maybe Excel can't read it because it's got like millions of cells, and you're just like, okay, I just need a subset of this. Let me load that data set into Python, subset on the parts that I need, and then save it back out. You can use LOC to subset things the way you want. So for the way I'm saying this phrase is going to be really specific, and so we're gonna use the tumor data set. We're going to subset the rows such that the value of tumor, the value of the group column, so we have to select the group column, where that value is equal to 1, and then we will subset this data set. So that column notation ends up being really important because we're selecting that column, seeing if that value in that column is equal to 1. If it is, that is what's being used to subset the entire data set. And you'll notice here at the bottom, we now have 97 rows instead of the 500, et cetera, rows. And when we get the first 5 rows and last 5 rows, you see that group is all equal to 1. So if I copy this, let's say we want multiple parameters that we want to filter on. So let's say we want to look at all of the baseline tumor sizes for the people in our control group. So in our people in our control group, that's going to be group equals to 1. What is the baseline starting size for all of our patients? Then we probably would want the values where day is also equal to 0. So the way we do this is we're using an AND operator. So this is like and also day is equal to 0. So this syntax notation is going to look very similar to filtering on group, we say tumor square bracket day, so we're looking at that column, is equal to 0. One of the weird quirks with Python is if you are doing, and one of the weird quirks with like NumPy and Pandas, not really Python in general, with this library, is if you have multiple conditions you are trying to filter on, each of those conditions have to be under a set of round brackets. Like, it's actually mandatory. If you don't have it, it will actually cause an error. And so now we have the values where group is equal to 1 and day is equal to 0. Let's say this isn't the actual data set that we want. We care about all of our patients, but we want to look at like the starting point and like some midpoint during the analysis. So how do we say we want the rows where where day is the 0 and also where day is equal to 13? The way we use the OR operator is using this vertical pipe. So it's like shift and then the key above enter on a US keyboard. And then we can specify another condition. It's going to work on the same exact column. So we say tumor square bracket day is equal to 13. So now we get the first, or the baseline day, and then day 13 of the study, and then for all of our patients in this data set. Okay. So now the question is, how do we subset both rows and columns all together at the same time? Well, there's two ways you can do this. The output of this notation, this LOC whatever, is actually a data frame. So if we wanted to subset on columns, all we need to do is go back to that first section on how do we subset columns. Well, given a data frame object, we use another set of square brackets, and then we can put in the columns that we want to subset. So this is subsetting on a data frame, but we want multiple, so we put in 2 square brackets, and then we can put in group, day, and then size. So that's one way you can do it. And this is one way where you can slowly build up your code if that's what you want to do. You can slowly start to notice, like, there's a lot of things going on in this code right now. So another way you can rewrite this code, and this is, if you're coming from the R world, this is sort of what the piping notation will look like. If you wrap the entire line of code in a set of round brackets, it doesn't matter how you put in new lines in this code. So you can say, like, I'm looking at tumor, I'm going to do a locating or subsetting feature, and then I'm subsetting by rows. So you can literally write your code in this format, and then it'll help you just vertically read down to figure out generally what's going on. So you can say, like, tumor, okay, you're doing some filtering, okay, you're doing some kind of column selection, and then if you care about the details, just keep reading right, or you can just figure out what's going on by looking down. The LOC function is actually more complicated because it's locating. It can actually locate on both rows and columns at the same time. So we can use LOC to subset both rows and columns all together. So just going back to this LOC, this outer square bracket is the way we subset on just this data frame in general. So just to make this a little bit simpler, so we're not using like this OR notation, let's say I am looking at, let's say I only care about where like size, the size column is greater than like 2000. So that is just regular row filtering. The way we can also filter columns at the same time, this square bracket technically has 2 parts to it. There's like a comma. The thing to the left is how you specify its rows, and the thing to the right is how you specify the columns. So if I also want, I can put in group, day with the capital D, and then size. and I can subset both rows and columns all at the same time, and it's literally, you have to remember there's a comma here. So that is really similar to R's notation and also like MATLAB notation. Any like matrix style notation, this is modeled off of that. All right. All right, so let's say I want to save out like a small snippet of my data set, right? So I have my tumor data set. I'm going to filter on both rows and columns. And let's say I only care about some of these columns, like the group ID, day, and size, but I only want the data set for the starting point and the midpoint. So I'm going to use LOC to filter my data. And then I'm going to say filter my data such that the tumor day, or the data set, the day is equal to 0. And because I'm going to add in another condition, I have to wrap it around round brackets. Or, in another set of round brackets, tumor square bracket day, the day column, is equal to 13. And then I'm comma. And then how do I subset my columns? I'm providing multiple columns, so I have a list object, so there's a set of square brackets there. And I'm filtering group with the capital G, ID with all caps, D with a capital D, day with a capital D, and size with a capital S. So let's say this is the data set I need for later on in my analysis, and this is all I remember on how to use Python for, or this is the only part that fits in the workflow I want to rewrite, because everyone else, it plugs into like something else that they need. So let's save this to a variable called filtered. And so now I have this saved, and I can do whatever I need to with filtered, right? So this is just a shorthand, so I don't have to rewrite that block of code. How do we go and save this out to a file? So remember, for a given data set, I can figure out what it can do on its own. And in Python, we use that with a period. So if I hit the period, there is a whole series of functions called to underscore. So we use pandas to read underscore something. If we have a data set, we can to underscore something. So we can literally take this data frame and turn it into something in our clipboard. So if you really want to like paste data into a spreadsheet like right away or some other program, like you can paste it, you can copy your data set into your clipboard, or you can use this to CSV function, or you can use this to Excel function, and then there's other formats as well. So if you literally write your tables in Python, like you can actually get LaTeX code to create your LaTeX tables. So you can do something like that. So I'm going to use the to CSV function. And then in here, we go back to all of that stuff about working directories and absolute paths and relative paths, because now we have to specify where do we want this thing saved. So I can call this tumor underscore filtered underscore py for python.csv. And CSV. Yeah. So right now it says like this data frame has no attribute like to CSV, and so that's my prompt that I probably typed it wrong. So it's to CSV, and then you'll see here nothing actually turned up as a result. But if we open up our data folder, or like literally go on your computer, navigate to your desktop, go here, go to your data folder, there is literally going to be a tumor filtered py file that just got created, right? So now I can email this to you or someone else, give it to someone else down the pipeline. If this is on a shared network drive or in a Dropbox folder, like it just worked and it just showed up on people's computers, right? So if that's one thing that you get out of today is like, oh, I can just save stuff out, fine. You've sort of created the first step in analysis pipelines. So analysis pipelines are really just as simple as data goes into a thing, and that thing produces another data set, and then that data set can be used for other things, right? So When people really talk about like, oh yeah, we have an analysis pipeline, hopefully that analysis pipeline isn't a single file that's like 3,000 lines long, and you just break up like the reading and cleaning into one file, and all it does is read in and save out, and then the next thing just does its next thing. So what I do a lot of times is I will have, if I'm writing a paper, I will have just the code that generated that one figure for that part of the paper, and the code in there is just related to that figure. And then the first thing that you'll see is I'm just reading data and then saving out the figure. And that reading data comes from other parts where I'm just condensing or calculating numbers. But this way, if I need to update the figure, I'm not trying to find line 3054. I just have the file that's properly numbered in a folder that says like figures, and this is figure like 3A. And I can just open that up, and then all I have is, this is the only code that's related to that figure, and that's all I need to work on. The nice thing about that is I don't have to rely on the previous 3,000 lines to execute properly to get to the part where I need to modify my figure. The data set was already written out, so assuming that the other parts are okay and you just need the figure updated, it's a really nice way to like generate figures and work with that, because inevitably you will end up in a situation where you need to update a figure. It relies on like many lines of code that you don't know what it does anymore, and it doesn't run from top to bottom anymore because something got updated or something changed. And all you need is to like change the figure legend, and you can't. And so that's why saving out things, I suggest you just do it. In an academic setting, like, that's probably okay. If you have like really large data sets where like just saving out things, like, you have to be a little bit more mindful of, yeah, there's other ways to deal with it, but for the most part, you can probably get away with just saving out like CSV files. Try to make it CSV files because it's plain text, so no other things can happen to it, and it prevents you from like just treating it as an Excel file, because there's a really big habit of like, oh, it's an Excel file, so I can open it and then like manipulate it, and then your plotting code no longer works because like you made a one-off calculation somewhere. And so that is actually what data pipelines are, is essentially just input a thing, and then that thing outputs, and then you can use it for whatever. Okay, we're actually doing really good on time. All right, so next thing, we're done with just the very big introduction to all of this stuff. So I'm going to close this notebook file. I'm going to click on, you can either click this little plus button, or you can open up another notebook file and it'll create another notebook file. And I'm going to rename this, and I'll call this, I'll just call this stats, because I'm gonna try to follow the same thing I did the other day. So what I want you to do for the next couple of minutes is run this sequence of things. Give me 1 second. I have to like make this pretty. Okay. So read in. So there is a data set called all.csv. So read that in to a variable called all. Select the first name, last name, day column, time column, and temperature and Fahrenheit column. And then filter the rows where the person's name is Anya Warner, and then save that out to a file named Anya Warner _pi.csv. I have the _pi because there's literally another file called with that, and I sort of just want to distinguish between the two. So we'll work on that for a couple of minutes. If you are done, I guess I haven't been in a live teaching setting in a while. I should have given you post-it notes. If you're done, you can just do that. In the Zoom side of things, if you are done or you are ready to move on, just type in the words like done, just so I have a sense of like you're ready to move on, regardless on if you're actually following along or not. And we'll also treat this as a break. So we'll sort of work on this until 55 past the hour. Okay, so let's go over this small exercise. And if you are from break, hopefully you're back. So one of the questions I got was, how can you change the working directory? So if you try to load up the all CSV function and it's not working like you expect, there is a command that you can run, and this is something that really only exists in the IPython Jupyter ecosystem. Mileage will vary depending on what is actually executing your Python code. But you can run a command called pwd. It stands for print your working directory. So we learned about your working directory. So this will tell you exactly where your computer thinks you are. And you'll notice that on Windows, it has the double backslashes because it's Windows. But this is where you are. If you ever need to change your working directory because for some reason this file was moved to a different location or you're trying to point to something else, you can, if you want to, change your working directory by using cd and then so for example, you can copy this thing, type in cd, and then paste that value in there. You can do that. I don't remember how you can copy and you can paste that in there to change the working directory. Just know that these two commands are not actual Python commands. So if you run this as like a Python script, not in this Jupyter view, it will not work. If you are in this folder, chances are the working directory is always tied to the location of this file that you're working in. So if, for example, you opened up your data folder and then you created a new notebook in this data folder, the working directory for that new thing you created is now the data folder. So if you want, you can literally close out of it and physically move the file to where you want to start off. But that's another one of those like weird quirks where like, hey, I went to this folder to look at it. I create a new thing and then all of a sudden like nothing's working properly anymore. So that's like another like quick fix if just to make sure that like things are pointed all in the same directory or all pointed or using the same working directory. Okay, so assuming that when you run pwd, it's exactly where you want it to be, how do we load up the all.csv data set? In this case, because we're starting off with a brand new notebook, we have to reload pandas. In pandas, there's a function called read_csv, and then we give it the actual path. For the CSV that we want to load. So if we run that, it looks like it loaded up correctly just by looking at the first row, which is I got a row of data and I have a bunch of column names. So I can call this all. And that's probably not a good name to use. I will call this all patients. I'll call that all patients. And so the next part was select just the first name, last name, just filter off those columns. So, and because I also know that I want to filter off of certain values for the rows, I can then say .loc, put a comma in, and then specify the different parts of it. So if it's easier for me to say first underscore name, last underscore name, day, time, temp, f, I can specify that. The LOC notation, if you, for example, want to use this to select all of your columns, the Python way of saying like select everything in this one axis, like all the rows, you have to put in a empty column that says like select all of my rows, but then filter off of all of these columns. But I also want to filter on a subset of rows, so I now say all patients. So how do we want to filter the values where it's Anya Warner. There's a couple ways you can do it. Because we're looking at first name and last name, we can say something, in this case, first underscore name is equal to ANIYA, and that's probably enough. Did I spell something wrong? Uh-oh, what did I do? Oh, my temperature. Oh, ha, thanks. I would have eventually got that, I guess. Okay, so thank you. So there's a couple of ways we could have done this, right? In this particular data set, there was only one person with the name Anya, so if we just said first name is equal to Anya, that's probably enough. For more complicated examples, we probably would have needed the round brackets and then an AND operator to say the first name is Anya and the last name is also Warner. So we have this part of our data set saved, so we can call this like filtered. And then the next part asks you to say, save the filtered data set into the output folder named whatever. So how do we save things? We can say filtered _CSV, and then in here we put in the actual folder that we want to specify. I already have this output folder created from literally yesterday, but if you try to do something like output underscore AnyaWarner.py underscore pi, it would have said you couldn't do it because the output folder doesn't exist, right? And so how would you go about and fix it? Well, you literally go and open up your folder and you like right click, new folder, create the output folder. Like the error message would have been folder does not exist, or output folder can't be found, et cetera, et cetera. So the way you fix that is literally go create the folder. You don't have to do everything in a programming language. Yes, there are ways where you can like check to see if the output folder exists. If it doesn't exist, make it. If it does exist, then go save it. You can write code for that, or literally just open a folder, right click new folder, and then just do it. And that, the other thing to keep in mind is like when you're creating projects and folder structures, like you can create like the folders that you need, even if they're empty, like that's totally fine, because if you know your code is going to use it, that folder already exists. And so that also builds into the whole data pipelining scenario of like, if you know that a folder is going to be used and it doesn't exist, like just go make it. All right, so I talked about filtering rows and columns. So now let's go and actually start the process of like doing some kind of analysis with it. I'm going to import. So if, for example, we were starting from scratch, I would say import pandas as PD. I'm going to load up that data set that we used for the pipelining example. So I'm going to say tumor underscore subset is going to be equal to PD dot read underscore CSV. And then we can actually go load up the data set that we saved off in the previous example, right? So like literally we are making a pipeline of analysis scripts. All right, so now that we have this data set, it is, if you remember, it was all of my, it's all of the data such that the day is equal to 0 or the day is equal to 13. Let's say I want an answer to the question, what is the average baseline tumor size across all of my patients? I need to first filter such that day is equal to 0. So I can say .loc tumor subset square bracket day with a capital D is equal to 0. And then I want the size column, so SIZE, and now I have a single value for just the size. This notation here gives me a series object, right? So if I look at it, remember the visual marker, if it looks like it's plain text and not a pretty table, it's probably a series object. If we look at the bottom, it's no longer telling me, it's not saying one column with 58 rows. It's saying like, here's a thing called size, and it's all like decimal pointed values. So I can say, let's save this to a value. I can call this tumor size 0. And because this is a series object, like a vector or just a sequence of numbers, if you're coming in from like the mathematical world, this is just a vector of values, which is different from like a one-dimensional matrix. So it's like just a sequence of numbers. Once we have this sequence of numbers, well, it's a sequence of numbers. Series objects know how to do basic mathematical calculations on itself if they're numbers. So we can tell it to say, hey, I want you to go do something, and that something I want you to do is go calculate the mean. So we can say, take the series object dot mean, and it will calculate the mean for us. So we can see that the mean tumor size across all of our patients at baseline, or day equals 0, is about 52, I'm assuming it's millimeters. So 52 of a unit that I don't remember. So another way we could rewrite this notation, so remember the a lot of times people try to compare Python to R and say like, hey, I don't like the fact that Python doesn't have that piping notation. Remember, you can wrap the whole thing around round brackets. And then literally the convention is actually putting the new line breaker in front of the dot. So you'll see code written, if my computer works, written like that, where you have your subset, you're doing some kind of filtering, and then calculating a mean. And so these, the process I did before and this process here is essentially equivalent to one another. All right, so now the question is, calculating everyone's baseline value at 0 is one thing. What if I want to sort of look at baseline values for each of my treatment groups? So I have treatment group equals 1, 2, 3, 4, et cetera, et cetera, et cetera. How do I go about doing that? So we can take that same block of code, and the simplest way is saying like, hey, I want the group is equal to 1, pull out the size column, calculate the mean, and you'll see that the hold on, give me 1 second. Okay. Let's do this for like day equals 13. Actually, do I want that? Hold on. I'm trying to think. I messed something up in my notes. I'm trying to like backtrack where I messed up. Actually, it's totally fine. So I'm pulling out the, give me 1 sec. Actually, this example doesn't make sense, so I'm actually going to have to do this. Yeah, Okay, so I'll make another one that's tumor subset 13, and it's going to be this tumor subset data that we just loaded up. We're going to subset such that the values of tumor subset day is equal to 13. And let's say the question is, I want to look at the size of all of my patients across each of my treatment groups, like midway through the study, right? So this is day 13 of the study. I want to look at the average size for all of the people in my control group. And what if I want to compare this value to all of the people in group number 2? So I could, in theory, copy and paste and change this value for each one of my patients, right? So you can slowly see, like, there seems to be a difference between all of these groups. And that's nice. That's one way where you can slowly start running separate calculations with different subsets of your data. The problem is, maybe this works if there's 4 groups in your data set. Not necessarily always going to be the case. So if you're depending on the data set that you're working with, what if there were like tens of groups? You've literally just copy pasted the same thing tens of times, which might work for the first time you're trying to deal with this. But the second something happens, like what if those group numbers got reordered or something, like you now have to, when you go back to change or modify things, because there's so much repetition in front of you, it's harder to catch smaller differences. Another thing is, what if you added another group? Right now your code doesn't, unless you also remember to copy and add the calculation for this group, if another group got added to your data set and you blindly went through this, you wouldn't have gotten the updated values. You would have gotten the updated values if more people got added to the same group. But if like a group 5 showed up or a group 8 showed up, like right now you wouldn't know. So if we just look at the tumor subset 13 data set, if we just look at the group column, this gives us a series object, and series objects also have this notion of give me the unique values. So let's say I'm presenting this in a certain order, and I'm assuming, like, let's say this is all you know. At least now you know, like, okay, if this is 4 and I can visually check 4, I might write a note to myself like, I only did calculations from 1, 2, 3, and 4, right? So if a 5 shows up, at least there's a visual prompt to tell you like, hey, there's something there. That's one manual way of doing it. But there's a better way because there's a lot of copy and pasting in here. And another thing that's sort of annoying about this format is I made 4 separate calculations. If I really wanted to like plot data on this, like I've gotten 4 totally like independent sets of numbers. Like I want a data set out of this. At the end of the day, I would like a data set that I can export out to a CSV or Excel file and then plot from Excel if I need to, right? So let's rephrase the question, statement a little bit, and this is important because the code follows the way this works. So for all of my patients from group 13, for day equals 13, so we're going to be working with this data set, I want for each value of group, I want you to calculate, so for each unique value of group, I want you to pull out that data set and then calculate the mean size on it, right? So the really important part of that is like for each unique value of, the coding syntax to deal with that form of like description is called a group by operation. So maybe you've also seen this in Excel as well. Excel has, once you click on the data tab, there's a way to like select group by operation. So if you could also in Excel say like for each unique value of group, pull out the size column, calculate the mean. So let's go and do that. So we have our data set. This is already pre-selected on day equals 13. What I want is for each unique value of group, so we're saying group by, we pass in the column that we want to group. And if we just run this, it says, okay, you ran a group by operation. I keep mentioning group by, what is actually going on under the hood. What happens with a group by operation, and this will apply to more complex programming in the future as well, is this notion of split, apply, and combine. So what I'm going to do is split my data set into each unique value of group, just like what I did before, which was this part right here, right? I'm going to split on each unique value of group. I have 4 values, so it's going to make 4 data sets under the hood for me. So split, apply, combine. The next part is apply. I want to apply a function, in this case, mean on the column size. So split, apply, and then combine is once you have those calculations, combine them together to give me a single data set. So split, apply, combine, group by. This is a concept that if you have access to a supercomputer and you heard about people like, hey, I took my code and I ran it across like 50 computers across 25 nodes, cores or whatever, like it's pretty much a group by operation in some shape or form. So group by. So once we have this group by object, the syntax is a little bit weird, but pretend that this is a data frame. We can use square brackets to say, give me the size column, and then calculate the mean. And so what we get back is one data set. In this case, it's a series, but we can also save out series as CSV files if we need to. And for each unique value of group, we got a single row for it, and then its calculated size. So we don't have to manually copy and paste things. We can say, like, you know the unique combinations of this, run these set of calculations for me. Okay. All right. So this is really specific to pandas and like series notation. What happens if you find like a function that someone else wrote or in another library and you want to use that function, right? So like we're talking about means right now, but what if you have like a column that like is not like one of these standard calculations? It's like a really specific transformation or a single calculation of some sort. How do we use other functions, right? Because you're not always going to be using something that's already built in. We want to be able to use some kind of custom stuff. I'm going to show you, let's say we realize that like NumPy is a library that deals with matrices, and it has a lot of functions that deal with matrices or just numbers. So NumPy also has like a mean function. So let's say we want the NumPy mean function, or if you work in Python, there's another library called SciPy that has a whole bunch of like optimization functions or other calculations. But let's say we want to use the NumPy mean function. How do we use a function that's not like built into pandas? So we can take this exact line of code, and instead of directly calculating the mean, we can say .agg for aggregate, or you can literally type aggregate. And so what is an aggregation function? There are many types of functions that work with numbers, have different like categories. One of those categories is an aggregation function. What is an aggregation function? An aggregation function is a function that takes in n number of inputs and it gives you one thing as its output. So mean takes in a whole bunch of numbers, calculates the mean, and the mean is one number, right? That's an aggregation function. Same thing with stuff like standard deviation. It takes in a whole bunch of numbers, calculates the standard deviation, which is a single number. That is different from a transformation function, like calculating a z-score, which takes in a whole bunch of numbers and gives you the same number of values that came in. So that's a transformation function. So an aggregation function is something that takes in a whole bunch, returns one value. So we use this to use other types of functions. So we can say AGG, and we can say pass in the mean function from NumPy. And so this is how you can use other functions. I believe if I say AVG size, yeah. So if you want this to be like more of a data set with like a different, like a proper name, you can actually simply put in like the new column name that you want to create and then assign that to a value. And now you see like things are a little bit prettier. And this is probably a data set that you can export out and work with. This is slowly getting to the part where like Python is getting more divergent from like R as a programming language, but something else that you might want to do, or this is another another format of this same thing. Let's say you want to calculate different, you want to use different aggregation functions for multiple columns or across different columns. So right now you see that we're selecting just the size column. So we only have the size column to create functions with. So if we get rid of this portion of filtering on just the size and pretend it's the entire data frame, we can still type AGG, and now we can say like average underscore size is equal to, and we're going to use round brackets, which is saying like, hey, I'm giving you a collection of things. So this is similar to using square brackets for list, but round brackets also mean like a group of things as well. It just so happens to be a group of things that you can't modify like under the hood. So there's a small difference between it, but you typically give it round brackets, and you say in here, I want to use the size column, and I want to use the mean function there. And so these are two different ways that you can specify using a function on a column. The benefit about the one I just showed you is you're not just limited to the columns that you have selected up here. You can deal with them later on. So if we build on this example, let's say instead of just looking at day 13, I want to group by the group column for each unique value of group and each unique value of day. So like a combination of these things, you can see if I go back to my original data set, instead of just filtering on 13, I can say for each unique combination of group and day, run this series of calculations. And so now I have group 1, day 0, group 1, day 13, and I'm running the calculations that way. Right? And this is way more efficient than filtering, doing 4 calculations, because just by adding in day, I've created 8 rows, so you don't have, so it's much easier to perform smaller units of analyses in your data. And why is that important? This is important because there is this notion of Simpson's paradox. So instead of just calculating like the raw value of something straight away, you have to be mindful that like just because if we look at this thing down here, just because there's some pattern that happens across your data set as a whole, for example, if it goes in a negative direction, if you look at subsets of your data, it literally goes in the opposite direction. And this is something that happens a lot in healthcare data if you like just group by age group, and all of a sudden like, wait, like it's the totally opposite effect, right? And so using the group by statement is a pretty good way to like look at subsets of your data instead of just taking everything all in one go. It's okay to look at, like it's called, at least from the world of epidemiology, it's called the raw statistic. It's okay to look at a raw statistic. This was actually the post that showed up on Twitter the other day. So this is the Simpson's paradox. It's okay to look at raw data or the raw calculation. For the most part, I will do this just to make sure my code works. But you have to be very mindful, like just presenting raw calculations probably is almost never a good idea because something like this can happen. All right, one thing that's kind of weird right now, if you use the visual prompt a printout to sort of prompt you of what's going on, you'll notice that like this data frame object prints out a little bit differently from all the other data frame objects I've shown you. Mainly, if I hover over, you'll see that like somehow it's like automatically grouping things. So like I have one value for group and two values for day. If this was like a flat data set, I would have one, like the group value for one repeated twice, right? So this is known as a hierarchical index, so like a multi-index. This falls into like something way more complicated in Pandas world, and this falls into the realm of like this was made for working with time series and stock data, and so that's why it's done like this. But if you ever end up in a situation where your data looks like this and things look kind of like not flat and it's like too pretty, what you end up doing is typing reset underscore index, and it will flatten everything for you, and now you're back to regular data frame world, and then everything I showed you now applies. So that's the main takeaway. This reset index was probably going to be your new friend. I pretty much do this all the time. Every time I see a multi-index, I get rid of it because I don't want to remember how multi-indices work. And again, the code here is getting pretty long. So I can wrap the whole thing around round brackets and then put in the new line breaks as needed, right? And so one, this saves me from scrolling to the right, and then two, hopefully I convince you that this is a little bit easier to read than like this, than what happened up before. And so again, you can look down to get a general sense of what's going on, and then look across if you need like more details about a specific step. The last thing I want to show you is what happens if we want a function that does more than take a whole bunch of input, give you a value. For example, there is a function called quantile or quantile. So I can give quantile a whole bunch of numbers, but I still need to give it like what percentage quantile cut I want to give it, right? So I can, like, for example, do I want the 25% quartile or the median or the 75% quartile or the 80% cutoff? Like, what is the value for that? That is a function that takes in multiple things in, gives you one number out. So it's still an aggregation function, but I still need to pass in additional information to it, right? So for mean, I don't really have to specify there's only one way you can really calculate a mean. There's multiple ways you can calculate like a quantile, because you have to give it the specific quantile you want to calculate. So how do we deal with that? So using the same code that we've been working with, in aggregate, if we have our code written this way, if we want to add in another function, all we need to do is separate it with a comma. And then let's say I also want to calculate standard deviation of size. So I can say size is using like NumPy's standard deviation calculator. I can do that as well. And now if I want to do something like calculate the Q25 of size, like the 25% quartile, or let's pick another like less useful one. So 33%, what is like the third cutoff value in my data set for size? So the function here would be numpy.quantile. Quantile. Right? So the problem here, if we look at the bottom, it's going to say something like it's missing one additional requirement for Q. So if I Google numpy quantile, so if I Google numpy quantile, I'll see the documentation for numpy.quantile. And here it takes some kind of sequence of numbers, so that's what I'm trying to pass in, but it's saying like I need to pass or specify this Q parameter. So it has to be between 0 and 1 because it's like 0.33 or 0.25 or 0.5, et cetera, et cetera. If I scroll down a little bit, there's going to be examples of how this is used. So given this sequence of numbers, give me the 50% quantile, and it'll give me like 3.5 across all of my numbers. I believe that's how that works. Yes. So I need to specify that queue. And this is sort of the thing that I realized right away, that Python is a little bit weird, and it sort of forces you to know a little bit more about Python as a programming language. I'm going to write the code first and then explain it. So this is, instead of rewriting this set of functions, so the way we have to call it is, if you notice, the way we call all the other functions takes that column of values and just passes it off into the mean function, the standard deviation function, et cetera, et cetera. Because quantile, we need to specify like something more specific with it, we have to essentially create like a custom version of that function. It can't just be like call quantile because it's asking for more stuff. So one way you can create a custom version of that function is using what's known as a lambda operation. And the way you can interpret this in your head is, I'm going to pass you a whole bunch of things. That sequence of things I'm going to pass you is going to be called x. And the way it knows that's going to be called x is because I'm using this statement called lambda. If you know a little bit more about programming, this is called an anonymous function. So it's a function that I am making up on the fly. This is a function that takes one input called x, and I'm passing in all of the contents of size to this value of x. What am I going to do with this value of x? Well, I'm going to actually call the quantile function, pass in that sequence of x, but now because I'm directly calling this quantile function, I can pass in all of the other parameters as needed. And so I can now say, what is the 33% cutoff for my data set by running this little block of code. If that doesn't make sense, that's okay. At least you have this here as a reference moving forward. But this will allow you to at least calculate more or custom summary statistics for what you need, right? So you can now create like your own summary table, and if this is what you want to export out, and then that is table 1 for your analysis or for your paper, then okay. So you can do that as well. The last thing that you can do, if you are working with just trying to figure out, like, I just want a quick setup or a quick set of calculations of what's going on, there is an actual function called describe. This is a method called describe that any data frame object can do. And for every single one of these columns, it'll calculate a whole bunch of like things for you, right? So if this is like the quick thing that you need, you can use this as well. So given my tumor subset, I can, don't worry about this column, as part of it is because of the way I saved it. But for group, you can see like there's 60 values in here. Group, because it's only 1, 2, 3, and 4, like some of these summary statistics don't really make sense. But for something like size, you can get like your mean, your standard deviation, min, max, and then all of your like cutoffs that you need for like for drawing box plots or something are all there. Actually, it's not really everything you need for box plots, but you get a general sense of like your distribution if you say dot describe, and then all of the columns that are like numeric will make sense. Okay, that is everything I wanted to cover for today. Give me 1 sec. So that's everything I wanted to cover for today. There is a set of surveys, again, like for pre and post, that you can go over there is a pre-workshop survey that you can still take until the end of tomorrow, which would be really useful. But for how does all of this stuff fit into the stuff that we're going to cover on tomorrow, if my slide deck will load up. So for tomorrow, I showed you today like mainly all of the components of like just loading in a data set, doing some quick set of calculations, how to just view that the data set that you loaded up is correct. Tomorrow is going to be talking about like, let's say you were manually entering data and it was in a format that was useful for inputting data, but you couldn't point to a column and ask the question like group by this column, calculate average of that column. So for example, if you were recording patients in that initial thing and you had like blood pressure readings in separate columns like BP1, BP2, BP3, et cetera, I can't actually calculate like for each unique value of blood pressure, for each like timestamp, blood pressure timestamp, giving the average blood pressure for all my patients, you wouldn't be able to do that. So tomorrow we'll cover like what does it mean to have a clean data set, how do you transform between data sets that are like useful for you for input and visually spot checking, or data sets that are like space efficient that fit well into tables, but then don't really fit well for analysis. That's what we'll cover tomorrow, and it all feeds back into like everything I talked about with spreadsheets today. And then once we have that clean data set, how does that all fit into visualization and model fitting? Because when you fit a model, you essentially have to say like, this is my output, this is my variable of interest, and these are the columns that I want to use as predictors for that variable. You have to be able to point to a column, and if your data set's not in that format, you can't do it. So the first thing that we cover tomorrow is going to feed into like pretty much every single step that you need for analysis, because it all requires your data to be in this very specific format for everything else to work. And then once you know how to like flip between the two, then you're less worried about like, oh, I know like I have to input my data when I'm curating in Excel because I can't do it otherwise. Once you understand like how you can flip between those two views, like life becomes much, much, much easier. So yeah, with that, that's everything I want to cover. Again, if you can, there's a set of pre-workshop surveys that you can take, and I'll see you back tomorrow. And if there's any questions, you can also just type them, and I will mention them and stuff.